This webinar will be divided into 5 main parts. We will talk about hull lines and how easy it is to create a sequence of hull lines. We will talk about the new extension in fairing direction and about the new hull line properties and the opportunities which come with them. We will learn how to create, modify and remove shell plates. We will generate production information for shell plates, having a look at the automatically generated roller line as well. We will inspect the elongation values generated by the system, and we will also create holes on shell plates and add bevels on shell plates. To get templates for our created shell plates, we will create a template set, save it, overwrite the template set we are not happy with, and also code both the template set and the shell plate containing the template set. Since 2016 T3, shell plates are visible in 3D context views as well, allowing us to create regular plates having relation to the shell plates visible in the view. The latest development in the shell module family are the new jigs. In this webinar, we will show how to use the system to generate an optimal jig plane, how to further use this optimal jig plane to create a jig view and to calculate and display the jig pillar heights. Let's create a sequence of hull lines. We go to construction, insert, and we choose hull line. The first tab that pops up is the definition tab. So by default the system has a sim. The first free number is 10. I'm happy with that, and yes, I do want a symmetric line based on starboard. The clipping area is the default one, calculated based on the view, and I'm happy with that as well. So I will go to defining the points of the hull line. I'll start adding fixed points. You can see that the system fairs the hull line, but I want to have a closed hull line, and in order to do that I check this checkbox here, and voila, we have a closed hull line. But I do want it to be perfect, so very nice. The points should be very symmetric to. So the first 2 points should have the same length. It is very easy to do that with multiple selection. We choose them and we say length on frame 24. The last 2 points have to have the same length as well, frame 25. The first and the last should have the same height. Okay, and the second and the third should also have the same height. Okay. Then I want all these points to be knuckle points. I select them all, and then I choose here the fairing time to be knuckle. Now we have square, but I would like that the corners are a bit more rounded, so I will choose here a radius of 100, and voila, I get a very nice closed hull line. And what I do now, instead of pressing OK, I will press on apply. What happens is that this hull line is created, and then I can go on and create a new one based on the one that I already created. So I already have this point selected, and I say, okay, I want a similar hull line, but a little bit further. So I will shift the hull line in the view with 200 millimeters. Oh, that's too little. I'll do 1000. And I have a hull line here. I press again and apply, and I get a new hull line. Then, so now I have 2 hull lines. If I shift this if I shift again, but now with 2000, I get another hull line. And I can continue like this, but I have 3, and for me that is okay for now, so I will press on OK. And now the dialog is gone. So to sum up, to create a sequence of hull lines that are similar, you just press on Insert, Hull Line dialog, you create a desired hull line, press on Apply, and then go on with the next one.
Another new and very important feature for the hotline are the new hotline properties. It is now possible to define hotline properties for a group of hotlines or for a separate hotline. These properties can be used to determine how hotlines are displayed in different views, for instance, the models used to mark them, and also they define the way the hotlines are projected on the shell plates. Let's have a look at the projection properties for the hotlines in my project. To inspect the properties, you need to go to your project, to your norms folder, and then to the CVAR folder. And here you will find the hlproperties.xml file. You should open this in an editor of your choice. I will choose Notepad++, and you will see here many rules and these properties. Let's dive in this first rule to explain what it means. The extra properties are applied to hotlines by selection criteria based on the lines key and the source. Therefore, you are able to specify filters on line type, in this case sim, line number, in this case all sims starting from 0 to 20, and line source. In my situation, I didn't use any line source, but the line source can be the user database or the shape database. As with other properties, all filters are read in a case-insensitive manner. So let's go to the properties part, the symbols. These symbols are essentially file names of models located in the models directory that should be used for the applicable lines in different scenarios. The default symbols are based on the line type. The system provides the following model: a sim symbol, a cut symbol, a but symbol, a DS symbol, a base symbol, or a general symbol. Each built-in model is also available in 3 different types: a PLV, CRS, and PRD model. Then, production properties specify the use of hotline in production. They can have one of the following values. They can be mark, cut, paint, sideline, baseline, or none. Default value for all these lines is mark, but these sims will be cut lines and are placed in the same layer as holes, that is the cutting layer, since both will be used in the cutting process. There are 5 projection methods to choose from. We have inside, that refers to projection on the inner shell plate surface. The inner shell plate surface is the one opposite to the shape normal. The outside projection property refers to projection on the outer shell plate surface that is parallel to the shell plate normal. The maximum, the one that I have used here, combines the first 2 projections, the inside and outside, and results in the outer contour of their union. This is intended for creating holes that guarantee that a solid with a given cross-section will fit through the opening. This property is invalid if the line is not closed as an outer contour and can only be defined for closed curves. Because we have defined a series of sims that are closed, we can use this property. There is also a perpendicular projection property, and this method projects on the working surface of the shell plate. And there is also a max perpendicular that refers to combining projections as for maximum, but ignoring the hotline's projection direction. Let's see a specific example of a function using this hotline property. Let's go to how. The symbols function has been also extended with a new option. You can now add symbols for hotlines. So we will choose the hotline symbol option, and the system prompts us to select the hotline. Let's select the hotlines that we have created before. We select the first hotline, and what you see here is a symbol. That is the symbol that we have defined in the hotline properties. To add symbols to the next ones, we just need to click and then click again, And we have added the symbols for all the outlines we have created. To stop the insert symbols function, we need to press on escape. The development done in the year 2016 for the new shell plate implementation totally changed the shell plate definitions and the unfolding method. This new method will not give the same results as the previous system. In the previous system, shell plates were generated based on the calculation lines, which were part of the input. In the new system, the keyword in the process of shell plate creation is simplicity. It is exactly as for regular plates by choosing the borders of the desired shell plate. So let's get started. We go to Construction tab, we select Insert Shell Plate, and we get the first panel where we can define the properties of the shell plate. I want a shell plate with a thickness of 10. The thickness direction is by default standard, meaning is in the direction of the shape normal. The non-standard direction is the reverse. What happens is that when the shape direction changes, the direction of the shell plate will also change. The offset is the distance between the molded line of the shell plate and the shape. The offset is a default 0, and it can have positive or negative values. I will choose an offset of 10, and we'll see that it will have a 10 millimeter distance from the shape of the shape. The default value for the shift of working plane is half the thickness of the shell plate, and we will leave it like this. The system automatically fills in the list of available material types, and it chooses a default one. I'm okay with this choice, and I press OK. The second step in creating the shell plate is to define the borders of the shell plate. And how you do that, you just select them in the screen. I select this hull line, this hull line, and this hull line. Notice that you can select hull lines from the user-defined database, but you can also select hull lines from the shape database, like this knuckle line. Now I press on OK, and you see here the shell plate, the generated shell plate. You see it has a distance from the shape. Oh, let's zoom in a little bit. See here. Then we go to the next shell plate again. Insert shell plate. I want again a distance, thickness of 10, and this time I will choose no offset. Press OK. Then I choose the hull lines, which I want to be the limitations of my shell plate. I press OK, and the shell plate is creating hull view as well. Now you can see even better that this shell plate doesn't have any offset. This one has the offset of 10. Okay, I go further. Another shell plate, this time a thickness of 12. It's okay. Shell plate relation. This. Okay. It appears in hull view as well. Notice the difference in color. This is due to the difference in thickness. Then I go again. Then I define the shell plate. Again, a shell plate with 3 borders. Press OK. This is the hull view shows the shell plate as well. And then again. Notice how this time I choose 5 borders. It doesn't matter, they could be 1 if it is a closed hull line, they could be 10, whatever is necessary. And the last one, this one is also going to be a bit thicker. Then I choose here. and it is here. In 1 or 2 minutes we have generated all these shell plates, and I hope you can notice that we have generated them the same way that we do for regular plates. In this new system, the algorithm will only use the shape surface to calculate the shell plate. It has the benefit that, as you can see, the plates will get their right form and contour on the shape. The module mathematically calculates even double curved plates into a flat pattern, taking care of the required shrink caused by the double curvature. Due to the accurate computation, shell plates can be developed without extra length. This method is very powerful, but it has also as drawback the fact that the user can no longer select calculation lines to avoid, for instance, unsmooth areas in the shape, making this new method susceptible to surfaces. It now requires a smooth surface to get good results. Also, all hull lines can be used to create the contour of the shape, whether it is user-defined hull line or hull line from shape database, and it doesn't matter how many borders the shell plate will have, the system still works. Like we have created a triangular shell plate, but we have also created the shell plate with 5 boundaries.
Now that we have created the shell plates, let's also give them some meaningful numbers so that we can easily identify them. To do that, we need to go to the Production tab, start the auto-numbering function. By default, we have a list with all construction items from the block, but because we don't have so many, I'll leave it like this. The numbering of the shell plates on starboard starts for 50. It's very good. And considering we do not have any shell plate on the starboard, I'll leave this edit field empty. Now I press on OK, and the system starts numbering the shell plate, showing a progress bar. It's very fast. Now it's done. In order to see the part labels, we need to update the view. We can update the hull and construction or the block or all blocks. And then we will see in the shell view the labels with the part number for the shell plate. Okay, so now we see the numbers for the shell plates. We have one shell plate 50 and it ends at 55, so we have 6 shell plates, and they all have now numbers which we will use further in the process when we generate production data and templates. Let's now generate production information for all the shell plates that we have created. In the same Production tab, we will start the function production information. We want to code only the shell plates for what we have created, and to do that we need to generate a list here with the shell plates. So we will choose a part list. Now our shell plates have numbers, so we can say the part list should have elements starting from 50 and ending in 55 from the current block, and then I press on create selection list. Now we have a list only with the shell plates, and we will create production information for these ones. Make sure that you have the no reference lines checkbox checked, because in the current version there is no reference lines for shell plates. We enable code block and we say OK. Now the system will generate production information for all the shell plates, but not only production information, it will also calculate the roller line and will generate the elongation report. In order to inspect the generated XF files, we will go to the function. Yes, we do want to save our view. And we will see here a list with the XF files for all the shell plates. And having part numbers for shell plates is very useful because it also it's used here in the name. This name can be customized. Okay, so we have very nice DXF files for all of the shell plates. Look also for the triangular one. Let's inspect one in more detail. These two lines here with the text MTR, this and this one, these are roller lines. The roller line is used to assist the folding of the shell plates, and that is why it is calculated when the shell plate is coated. The definition of the roller line is such that it can be useful to both supporting forming methods, to both cold forming and line heating. The text that you see here is also customizable. To do that, you need to go to System Management, to Production, plate cutting data, shell plates, and settings. We have here the roller line text. You can change it to the useful text for your company, and the roller line grid distance. This is a value in millimeters used to define the grid spacing for the roller line. This one can be also customizable. There are two notes to be taken into consideration regarding this roller line distance. A roller line will not be calculated if the value is below 100, and if the shell plate is not big enough to support the current grid spacing value. The system is so smart as to halve the value until a grid of at least 3 lines fits, or the distance becomes less than 100 millimeters. So imagine that here we would have had a value of 500 millimeters. If you are coding a smaller shell plate, then this value will be too big. What the system will do, so he will halve the value until it finds the right one, unless it goes under 100.
In order to provide the necessary information to deform the flat plate to its final form, the system is able to generate an elongation report. This report consists of an XSLX file and is created during the coding of the shell plate. This report can be extensively configured by using a template XLS file and a handful of settings in the system management. Let's go now to the report to see what it has. So in the project you are working on, in norms cbar, you will see this elongation report XLS file. So this is the template that will be used to generate the elongation report for each and every template. The report can roughly contain the following items. So we have the shell plate logistical information. We have elongation map images. By default, in our standard norms, we have the horizontal elongation and vertical elongation. For these images, we also have the color legend explaining the images, and a 3D image of the bent shell plates with templates if templates are available. The template is scanned for images in the upper left top corner in a cell containing specific commands. The reserved commands are, like you see here, image strain X, image strain Y for the vertical elongation, and it can also be image strain XY and image 3D. The image strain XY will display the deformation values, telling us how difficult it will be to bend the shell plate. The image 3D is, of course, for the 3D image of the shell plate. Together they trigger the generation of the corresponding image in the end result. The position and dimensions of the image in the template XLS are recorded so that we can position and size the final image. These images, without one of the reserved keywords, like here for instance, can be used to, it will be transferred as they are and can be used, for instance, like here, for a company logo.
In the elongation bitmaps, the flattened shell plate contour is depicted in black, and the marking lines of the inner construction templates are depicted in white. The remaining of the shell plate surface is filled with colors depending on the local elongation. The local elongation is transferred to a color by using defined rules in the system management, which we will see in a moment. Since the maximum elongation that is allowed usually depends on the logistic data such as thickness and material, we will use these logistical informations and they will be displayed here. The color legends, they also have here keywords, so they are positioned between the cells with this comment x call or y call. These keywords should either be in the same row or in the same column. The amount of cells between the keywords determine the step size of the legend. So from first to until last, we will have so many colors in the legend. The test cells are filled with linear ranges between the extrema and are returned by the rules. Similarly, the color cells are filled with the color corresponding to the average of such a range as returned by the color rules. Cells in the template without command are copied as they are. Cells with valid command are filled with the text resulting from resolving those keywords in command. The valid keywords in the command are the usual general ones and the logistical fields of the shell plate. When we go to the shell plates, the system has generated an elongation report for the shell plates as well next to the DX file, and that report was done based on the template that we have just examined. So let's go and have a look at how the report looks like with our shell plates. The elongation reports are located in the block folder where the shell plate is created. If we open this one, you see here that it looks like the report, like the template that we have just investigated. This shell plate doesn't have very high elongation values, which is normal. The plate is quite straight. We see here the logistical information of the plate. The shell plate is the one with the part number 50. Here the logo of your company, and then the legend for the colors. You see there is a one-to-one correspondence between the elongation value and its color in the legend. Let's also have a look at a different one. If we open this one, okay, here we have a little bit more variation. We notice that there is more vertical elongation than horizontal. And if we look at the colors, you will see that they correspond also to the legend colors. These colors can be added in the system management. The elongation list settings are located in production, shell plates elongation list. And here you can edit the general settings, you can edit the color and transparency, or you can modify the rules for the color map for both color and extrema rules. If we modify the general settings, here we can edit the horizontal and vertical spacing. Please be aware that when modifying these values, for instance, when you want to have the values per frame distance, and you would have the frame distance, let's say, on 700, then the colors from the color map will not correspond anymore with the elongation values. So if you modify these settings, only use the elongation values as a guide and not the colors, because those are drawn always in square meters. But you can also modify the report name. For instance, you could use the shell plate part number instead of the shell plate key, or you can use another label unit system. Next, we can edit the colors, the color and transparency. Here we can modify the color used to draw the shell plate in the 3D image and make it transparent or non-transparent. And we can also modify the color used to draw the templates and those to make them also transparent or non-transparent. And the next settings are the rules. We can modify the color mock color rules. So if we open this, then we see my existing rules, the ones that I used in my elongation report. You can add new rules, you can edit, and to edit there are a lot of helpful fields. So if you choose one function then and you press insert selected text, then this will be added here. So if we press on insert selected text, then you see it in this field, but I don't want it to do now, will not save it. You can also choose the logistical fields, and you can use the variables that will be used, constants, and also operators. No. Information say continually, yes. The same rules can be also modified according to your needs for the extrema rules. If we open this and then we can say add, and here you can choose the rule that you want. So these are the settings for the elongation. So the settings together with the report will help you to define the elongation report needed in your company.
There are also other settings in system management which will be used when generating production data for shell plates. For instance, we have in production plate cutting data some settings for shell plates. So if we open the settings, we don't only have here the roller line settings, but we also have a sideline presentation or the method of forming option. This is very important. This will determine how your shell plate will be formed. Then we have in production plate cutting data DXF output, the settings. These are the general DXF settings for plate cutting data that are applied for shell plates as well. As a general rule, if there are no separate settings for shell plates, the settings for plates include both plates and shell plates. So that means that also the marking line settings will influence the shell plates as well. So even though we set them for plates in general, so all the settings here, if we go to plates, these settings, for instance, will be used for shell plates as well. So let's go back to our DXF file. Okay, production modify coded, and here we have again the list of DXF files for our shell plates. The last item I wanted to show you, to explain actually, is this are these green lines here. What these green lines are actually the hull lines we have created before, the sequence of hull lines we have created by using the apply button. And why are they green? That is because their production property is defined as cut. So the system will use the cut properties when coding these hull lines. They also have the special symbols here. These are again the symbols that were set in the hull line properties for the production. Of course, it doesn't make so much sense because here we have construction, but what we are doing here is a little bit academic. Doesn't have to be followed for shell plates that are made in real life. Let's go now to the next step, that is creating holes in shell plate. To do that, we will need a shell view. Let's create now a new shell view. We will create a side view. Let's increase this height a little bit. And we press on create. Okay. To create holes in the shell plate, we need to go to Construction tab and choose the Insert Shell Hole function. We will start here, and the system prompts us to select the closed hull line. In order to create a hole in the shell plate, we need to use closed hull lines. We will choose now the first hull line, the first closed hull line we have created before, and the system starts to calculate the hole. Okay. Once the hole is calculated, it is also visible in the hull viewer as well, not only in the view. So what we see that in the shell view, we have this blue circle indicating the existence of a hole in the shell plate. We can investigate information about this hole by using the item information function. Okay, so we see that we have here a hole in the shell plate that is in block 108. Okay, let's now add more holes in the shell plate using the other two closed hull lines as well. So we go to Insert Shell Hole, we select the hull line, and the system will start calculating. What is important to know is that when calculating the hole, the system uses the projection property of the hull line. So the one that is mentioned in the hull line properties XML. If you remember, we have used for this seams that we have created here the maximum property. This maximum projection property, it is a special projection property made with dedication for holes, because as you remember, it is a combination of the inside and outside projection. The inside projection refers to projection on the inner shell plate surface, that is opposite to the shape normal, and the outside projection refers to projection on the outer shell plate surface, that is parallel to the shell plate normal. The result is the outer contour of the union. This way you can fit a solid in the given cross section through the opening. And this projection property is only logic to be used for a closed hull line. So if it is used for a non-closed hull line, the system will give error, it cannot use it. So let's add a hole to the last shell plate as well. Okay, now we have 3 holes in the shell plate. The holes are binded to the hull lines that is used to create them. That means that if we modify the hull line, the hole will be recalculated as well when we recalculate the shell plate using the new hull line. So let's do that. Let's modify this hull line here. Modify hull line. Yes, we first need to save our drawing before we can modify a hull line. And then we say save. Yes, overwrite it. Okay, modify hull line. We select the hull line. We say okay. What we will do, let's shift these 2 points a bit. So if we say minus 100. Okay, you see that now the hull line changes. We press on OK. and now we have two contours here. This is of the old hairline that is being used for the hole, and this is of the new hairline, the one we have modified. What we will do now is that we will recalculate the shell plate. We say OK, and what happened is that the system recalculated the hole that we have created, and now the hole follows the shape of the updated hairline. Okay, to summarize, if we want that the hole will be updated with a new hairline, then we will need to recalculate the shell plate. By recalculating the shell plate, the hole will be recalculated and it will use the updated hairline. It is also possible to remove holes in shell plate. To do that, we will use the remove construction function. And now we can select any construction. We will select the hole. You see that the system gives a preview of the selected hole, and we say OK. What happens now is that the system again recalculates the shell plate because the hole is gone, and the shell view will be updated and the hull viewer as well. Okay. So you see that the hole has disappeared from the view. There is no blue circle anymore, and it is also now removed from the hull viewer. So the model of the shell plate is the hull viewer model of the shell plate is recalculated, and the hole is gone. We have now removed one hole, but you can also remove multiple holes in one go. We go again to remove construction. Here in the label you can choose what you want to remove. So in our case we will say we want to remove shell holes, and we have this very handy function called all, and what this does, if you press it, it automatically selects all holes in the shell view. We can highlight them again. Okay, these are the holes, and let's press on OK. Now these holes will be removed too, so the shell plate is recalculated again. The hull viewer is updated when the recalculation of the shell plate finished, and the views as well. So now we have no holes anymore. But if you want to retrieve some elements you have removed, in our case we have removed now a whole construction, there is also an existing very handy function here in remove called undo 3D removal. So if we press now on undo 3D removal, the last holes we have removed will be re-added. So now again the shell plate is recalculated. The holes will appear in the hull viewer, and they will appear in the shell view as well. So we will see again the circles. We say now update block, and we have back the holes. So if you don't believe me, I will demonstrate. If I go to item information and I select, let's say, this hole here, then you see it is back. I want to mention three other issues regarding the holes. The first one is that if you have a symmetric hull line and you have also shell plates on both the starboard and port side, the system will create a hole on the side that you choose. So when you select the hull line on the starboard side, it will create a hole in the shell plate from the starboard side, and if you select from the port side, it will create on the port side. The second property which I like to mention here is not visible, but the hole, the contour of the hole has has the color of your settings. In my settings now, there's a coincidence between the color used for the seam and the color used for the whole contour. But if we would have had the dimension line, for instance, that's for me white, then the contour of the hole would have been red on top of the white contour of the dimension line, so you can very easily distinguish between those two. And the last but not least is the holes in shell plates are currently not visible in outfitting, so only in hull.
Shell plates, like regular plates, can also have bevels. The Insert Single Bevel functionality is available in the shell application, and it works similarly to the one in 3D Contact. In order to start it function, you need to be in a view that is not a 3D aft or a 3D forward view. In these types of views, it is not possible to add bevels. The first step is to start the functionality and to choose the shell plates to which we want to add the bevels to. In our case, let's go somewhere here, and we will add bevels to these two shell plates. Selecting them is very easy. Selection box. You can also highlight, to make sure you're choosing the right shell plates, and press on OK. The system offers a preview of where the bevels will be placed, and this is in our case where we have selected. I will choose now a V plus bevel. You can continue to modify the properties of the bevels, and I will now disable the relative angles and press on OK. Now the bevels are added where we have selected the shell plates. A bevel is both an attribute that belongs to a shell plate as to the involved relation, just like bevels on regular plates. Bevels have direction. For example, in our case, V plus means that the opening is at the shell plate thickness side. Also, note that the contour of the shell plate is taking into consideration the bevel. Presentation of the bevel is done in fragment 78 with the pen 4. Bevels are presented only when they belong to a solid block or when the environment show-bevel has been set to yes. Presentation depends on the setting, presentation, bevel settings, presentation type. So if you have set the setting to text or model and text, the text will be presented. And if you have set to model or model text, you will see the model. The bevels can also be modified if you go to modify bevels function. They will also be updated in case that the particular shell plate to which they belong to will be recalculated and updated in the current view. So a shell plate is recalculated if, for instance, its relations are changed, if its properties have been changed, if it is selected using recalculate construction parts, or if the recalculate all function has been used. Coding of the bevels on the shell plate is also completely analogous to the one on the regular planar plates, and removing a bevel is part of the remove construction. And here you can very easily remove only bevels so that you avoid making mistakes by selecting other construction by using the selection list. So you say, okay, I want to remove bevels, and from now on also very easily select them, and you see that if you highlight, the system only selects bevels. This way you don't remove accidentally some other construction parts. I will not remove them now. So this is how the bevels work for shell plates. You can notice it is completely similar to the bevels on a regular plate.
In 2016 T3 release, we have added another useful function which relates to hull lines and shell plate. That is, the possibility to define a paint line and calculate the distances from this paint line to the edges of a shell plate onto which it can be projected. The paint line is used, as the name suggests, to define the paint areas between the hull line and the edge of the shell plate. Therefore, the first step is to define a paint line. The way to do this is, of course, by means of the new hull line properties XML file. Let's go to the hull line properties XML file from this project. We have it already open here. I already have in my XML rule that defines a hull line as a paint line. We need to find it, and it is here. The way to define hull lines as being paint line is by using the production value paint. We offer in the default hull line properties XML already a rule that defines paint lines, and that is dimension lines that have numbers from 900 to 910. We also provide default symbols, but as you already know, you can change that. So you can change the symbols, and you can change also the rule, like I have done here in my project. Okay, so now that we have a rule that defines paint lines, let's also create a hull line that qualifies to this rule. Let's go back to hull. Let's insert a dimension line, and we have seen in the rules that the paint line has numbers between 600 and 620, so I'll use 601. And then we need to go to the point step to define the points. Let's choose a shell plate for which we will calculate the paint line distances. Okay, let's do on this shell plate here. We insert points. Okay. Together with this function, you can use another new utility function, a new property actually for the points that we have introduced also in 2016 T3. That is especially handy where you're defining, for instance, a paint line when you're defining a paint line for the whole ship. You can use this extension in fairing direction function, which will shift this point in the direction of the fairing. So it will extend the line in the direction of the fairing. So let's extend this point here with a value of 500. Okay, so you have seen that it was moved in the direction of the line. There are two types of direction that it will use, outgoing and incoming. And that is depending on the point you are going to extend to. Because this is the first point, it only makes sense to have the outgoing, and this is, if we will do to the last point the same, we will need to change to incoming. Say 500. And now we have defined our dimension line. If you want more information about how this function works, there is a help about it. Let's save it. We press on OK. And now we are ready with the first phase. So we have defined a rule that defines a paint line. We have a hull line that qualifies as a paint line. And now we want the final, and that is to have the distances. We need to go to draw, more dimensions, and we have here this function called paint line distances. Now the distances will be computed for all paint lines and the shell plates present on the drawing, and on all grid coordinates present in the view, that is the grid coordinates of the x-axis of the view. These distances are calculated on the thickness side of the shell plate. And Now the function is finished. You see that they are also indicated in a very intuitive manner. So we have here this line with arrows that indicates clearly that from the paint line to the edge of the shell plate there is a distance of 490 millimeters, and from the paint line to the other edge of the shell plate it's 899. If we zoom in, you will see here that the arrow is not exactly on the edge of the shell plate and here of the relation, and that is again because the distance is calculated on the thickness side of the shell plate. So if you save this view, because these elements are 2D elements, they will be saved as well. So if you save the view, this will be saved, and it can be used on the when the painting will be done in the end. If you want to remove these are 2D elements, so you need to just select them, press on delete, and they are gone. Together with a completely new shell application, we have also introduced the possibility to visualize the shell plates in 3D contact and also use them as relations when creating regular plates, for instance. So let's switch now to 3D contact.
We will create now a frame view. We go to create frame. We will create on frame 26, and notice that we have now in the panel a new option called show shell plates. By default this is disabled, so you will see the hull line and not the shell plates in your view. I will now enable it, because what I want to do is not only show the shell plates in the view, but also create a regular plate that will have relations to the shell plate, so it will be related to the shell plates and not to the hull line. When the shell plate is changed, the plate will be updated as well due to the topology between the two. I press now on create. And we see now a clear difference between this part and this part. Here we have shell plates, and here we have the hull line. Here we did in this area we didn't create shell plates, so there are no shell plates to be seen. But in this area here we did on this part of the hull. In modify properties of the view, you can disable showing the shell plates, so you can see again the hull line. In our case we won't do that because we will create now the regular plate related to the shell plates. How you do that? Just the normal way. You go to construction, plate. Now we'll create a plate in view with a thickness of 10. And the rest is also business as usual. We choose the relations, and now we will choose the shell plates. We have multiple, so we choose them all, and I say OK. Now the system is calculating the shell plate with the plate with relations to the shell plate, and we will also see it in hull view. You see now there is nothing there yet, but once the plate is created we will see it showing up in hull viewer. Yes, here it is. We have it also in hull viewer. So you see now that the plate is very nicely following the shell plate. See here. The system has also added the natural bevels. Yeah, in my case eye bevels, because that's how my rules are set up. The natural bevels will follow the rules that you have set up, but this is another subject. We won't go into details now. So in a nutshell, this is how you create now regular plates that are related to shell plates. Just enable seeing them in your view and continue working and create the shell plates, the plates.
Okay, so we have gone now through all new aspects of the hull lines, through all new functions of the completely remade shell applications and the new possibilities. Let's now go to the templates part. The previous templates application had quite some drawbacks. The templates were created very big, making them difficult to handle and causing a limited side plane. The relation between template and shell plate was not clear, using a lot of searching, which costed extra time. There was no standardization information in drawing, causing again increase in time searching. And even more time was needed to learn to use the user interface because a specialization was needed, causing again a time-consuming learning curve. We have used all this information when creating from scratch the new interface. With the new templates interface, we can now create maneuverable templates in a very simplified manner.
To create templates, we need to go to the Template tab, press on New, and this will start the new template set panel. In this panel, we can choose the shell plate or shell plates that we want to use. If we choose one shell plate, we can create templates set for that shell plate. Currently, there is no possibility to create templates for multiple multiple shell plates. So let's choose one shell plate. Let's choose this one, and let's create templates for it. Now the Create Templates wizard appears. We call this panel the Templates wizard, and this one allows us to create a template set in the manner that we want to. So we can do in this panel all modifications that are necessary in order to obtain the templates that we want. In the first tab of this panel, we can manipulate the side planes, the sideline plane, and the offsets of the first and the last template. As you can see in the hull viewer, when this panel starts, the system uses all defaults and it calculates automatically the default templates for this shell plate. So what you see in the hull viewer is only a preview. Now the templates haven't been created. By having this preview, you can, whenever you change something, you see what happens, how they will look like. So the side plane. You can have two side planes. If you choose to have the outside side plane, then the system will create templates on both sides of the shell plate. I will click it here so that you see. Now we have two side planes, and you also see a preview of templates on the other side as well. But I do not want to create templates on the other side for now, so I will check this out again. Okay, you can modify the offset of the side plane. If we say here to 200, what you see now is that by doing this, you modify actually the height of the templates. This offset is the distance from the default side plane position. The default side plane position is easier to see than to explain. So if we change the offset to 0, you see now here that the side plane it touches this end of the shell plate, and that's its default position. So if you want to check it, just set the offset on 0. Let's put it back to 200 now. Okay, so and also with inside and outside, we mean the position is either in the direction inside or outside of the ship.
The default position of the side plane is on the 50% in the middle of the edges of the shell plate. You can also modify this. So if we say, okay, I want it at 70%, the start position should be 70% of this edge of the shell plate. You see also in the preview, in the hull viewer, that the preview is updated. The template's offsets are used to specify an offset from the edge of the shell plate for the aft and the forward templates only. The offsets are used to place the aft and the forward templates within the edges of the shell plate. The default value that you see here is 2 times the plate thickness. And the offset, of course, can be only positive, and there is no limit defined for this value. The Method tab. This tab allows selecting the method in which the template should be positioned. There are 3 types of methods: on grid, angle to side align plane and side plane, angle to sideline plane, and shell plate. The on-grid method, using the on-grid method, the templates are positioned along the grid coordinates, like here, length to width of height. When the template wizard is opened for the first time, the default grid dimension is calculated based on the position and shape of the shell plate. For example, along the length, if the length is the maximum of length, width, and height. Then, angle to sideline plane and side plane. Yeah, these are quite self-explanatory here. If we choose one of these methods, so if we choose this, then we can modify the angles that are being used. So for angle to sideline plane and side plane, we can modify the angle to the sideline plane, and the angle to the side plane. These angles being 90 by default. If you choose on grid, of course, there are no angles to modify, and you see that they become deselectable. Now that we are here at the Method tab, let's also talk about this option here. By default, this option is not selected, and what it means is actually choosing the type of relations that are going to be used when creating the template. So what kind of relations are going to be used in relation to the side plane or the shell plate. There will be 2 types of relation used, and one is perpendicular to the side plane. This relation will be used when we check this option. The template will be then created using a 90 degrees relation to the side plane. And the default value is not to have this option enabled, and what will happen is that the system will use a perpendicular relation to the shell plate, and using this relation will mean that the template is created using a 90 degrees relationship with the shell plate. The default method is that you see here. You saw that by default the on-grid was selected. This is specified in a system management application. So, because this is very important, I will abandon the process of creating templates for now and show you where this option is located. So, we need to go to System Management. To Extra Shell, and we see here, okay, the help. We see here the template default method that is in my case on grid. So you can change it if you want as default another method. Just change it here. Okay, so let's go back to creating templates. We need to open the block. Say open. Ooh, Sorry. Let's select shell view. Okay, let's go to template, new, shell plate 51. Okay. And let's go to the distribution tab. The distribution tab allows setting the exact position of the templates. The spacing refers to the templates being spaced from each other using a grid or giving a distance. By default, it has chosen a grid, and it chooses the optimum dimension here, and that is length. If we choose distance, then we will have to use millimeters. I will not do that now. I want to use grid values. So the system calculates default templates. So the first is the first template position on the start point of the sightline, and the last is the last template position corresponding to the end point of the sightline. The step is the step in which the middle templates are positioned, and the amount is the number of templates. So let's say we modify the step that we use, well, half a frame instead of one. Okay, now the frames will stop to the templates will stop to 26. So you see now also in the preview, and if we change this back to 1, okay, we end up at frame 30 again. So the system, whenever you change a value, it will recalculate the other ones as well. Very important to mention is that there will always be templates on the start and end point of the sightline, unless the user has removed their presence. And how you can remove, we will see just in some seconds. But this means that the amount that you see here is the amount of templates between the first and the last mentioned here. So we actually have 10 with the aft and the forward. The last tab in the Templates Wizard panel is the Properties panel. In this panel, you see a list with all the templates, so the first and the last, and also the after and the forward template. The first template here corresponds to the first one listed here, and the last one corresponds to the last one listed here. So these are the first and the last templates on a whole grid value. In this properties panel, you can select a template. For instance, we select this, and you can modify properties for it. Because our method is on grid, these angles cannot be edited. So the difference between this properties panel and here, the method here, is that if you have, for instance, chosen one of these methods with angle, if you modify an angle here in the method panel, this modification will apply for all templates in a template set. So let's change this angle here to 60, for instance. And what you see is see that all templates have changed now their angle to the side plane. Now, if I go back to the Properties tab, you see that they all have now the angle to the side plane to the side plane to 60. So if I modify now only for this template and I set it to 90, you can see that it's only applied to this template. What you can also do in this panel is you can enable or disable some templates. So using the distribution panel tab, you create a list of templates using some rules. But here you can say, okay, some of them I really don't want. So for instance, if we disable this one, then it's out of the preview. You see it doesn't exist. So when we will also create the templates, this template will not be created. So let's now press on OK. Now the system is starting to calculate a plate for each and every template that we have defined, except for this one, because we said we do not want one plate for this one. You'll see the templates also popping out in the HAL viewer once they are created. So every template has been created. Okay. We see that for the one that we have set as present, no, there is no template plate created. We have a template plate for the sideline plane and for the plates. With the help of the wizard, you can create every possible template, whatever is necessary for your needs. By creating them, now we have templates that are real plates. They behave, of course, like a regular plate, so we can ask information about a template. If we right click on this template here and we ask for item information, then we see that it is the template on frame 25. Yeah, its neighbor is missing because we chose not to have there one. What you see here in block, this strange number, this is what we call a temporary block. When you're creating a template, you're in a temporary block, and once you save them, they will become part of your active block. So this is how our templates look like. What you can also do, you can ask for item information of the site line plane. There is no difference. The default description is SLP from site line plane. If we look at attributes, in the extra we see the plate relations, and in the geometry we see the regular information regarding a plate. What we can also do is we can create a view, a perpendicular view from template. So if we choose here, create new perpendicular view, a new view will be created in a HAL containing this template plate. Okay. Here, having the template here, you can modify its relations. If you start the modify relations function and you choose the template, then the modify relation function pops up. But I do not want to modify now the relations, but you can do it if you need to do that. You can also insert arbitrary holes. You can, of course, also use the other functions. You can code the templates, what we will do in an instance. You can again use the regular item information function. Yeah. Logistics, the template on frame 25. Okay. Let's now save the template set that we created, and in order to do that, we press on save. The default name of the template set is the name of the shell plate that has these templates, for which we have created these templates. The system also displayed the shell plate the templates were created for, and it prompts us to choose if we want to save production information or not for these templates. If we choose yes, when we code the shell plate, the templates will be coded on the shell plate as well. If we choose no, when we code the shell plate, the templates will not be coded on the shell plate either, so they will not be marked on the shell plate. But I do want to have them marked on the shell plate when I code the template, so I say okay. What I want to show you, so if we do again save, suppose that we have done some changes and I choose the same name. If I press again of OK, I will overwrite the existing template set. So if you have made some mistakes and you want to change it, just choose the same name. What will happen also is that the system will display the existing template set in the current block. We only have one now, but if we have had more and you want to overwrite a specific one, you can select it from the list. Okay, so I do not save again because I've saved it already. What we can also do now is code the templates. So if we start the code templates function, we can code all templates in this template set, whether in a batch mode or in a regular mode. If we do it in a regular mode, then the system will be calculating and we cannot do something else. If we do it in a batch mode, we could do something else in the meantime. I will do it in a regular mode, so I press on OK. And now the system starts calculating the DXF files for all templates. Of course, this takes a bit, depending on how much templates you have, depending on their complexity, etc. Okay, the coding has finished. Let's see the results. For that, we go to Modify Coded. Yes, these are the shell plates we have coded earlier, and here you see the DXF file for every template, for each and every template, also including the sideline plane. You can see that the DXF file have very intuitive names. That is the name of the template. If we have a look at the DXF of all files, you'll see them here, full templates, also the sideline plane. Here, what you also see are two symbols indicating how the templates should be positioned. You also see here the intersection with the sideline plane. This also has a special symbol. If we go now to the sideline plane DXF, you will see that the two symbols are present here as well. So the purpose of adding the symbols to the coded templates is to provide information on how to place the templates on the shell plate during production, since the same markings are present on the shell plate as well. Positioning the templates such that the markings match ensure correct placement. What you also see is, you see the regular markings. Here is the block number, so you see that here you mark the current block and not that temporary block. So that's only to help creating, but the templates belong, of course, to the regular block. If you are done creating templates, then you can exit the templates function by pressing the close button. This button will ask us again if we want to save. We've already saved, so we don't need to save it again, so we say no. What happens is that we are out of the templates function, out of the temporary block, we are again in the active block. and in the shell application. So we could now create shell views and create shell plates. The view coded part is available in shell and also in 3D Contec. In the shell applications, if we want to use the view coded part function, we need to go to production information and then to results and code or block. Here you see a list with everything that has been coded in the project. Here at the end is listed an element for the template set that we have coded just before. To identify, you need to search for a T, meaning that comes from template, and what is after the T is the key of the shell plate. So if we select this here, then we will see a list with all the templates that have been coded in this template set. By selecting some element from one of those, one of the lists here, we visualize the template, the coded template in a hub. So that's how view coded parts works. To reopen the template set, of course, we need to go back to the shell application. We go to the templates tab and we have the open option here. If we press open, the system will display the list with the template set present in this block 108, the current block now. So I choose the only template set I have. I say OK. And now the templates function is started again. You see here again the template block, the temporary one, and again all the regular functions are activated and can be used. So you can now do some modifications to your template set, then save it if you want in another name, or overwrite the existing one. As you can see, when you open the template set, then the template plates are also loaded in the HAL viewer, and you can perform whatever modifications are necessary. We are not going to do now any modifications. It's for the purpose of showing how it works. I'm going to exit the templates function now and show you how the templates are marked on the shell plates they are created for. So we'll exit the templates. We won't save because I haven't done any changes. Then go to production, production information. And I don't want to code all shell plates. I just want to code the one we have created templates for. So I recreate the parts list. I will say here I only want for shell plate 51. Okay, don't forget to choose the no reference lines, since in this current version there are no reference lines for shell plates. We press OK. And the system will be coding the shell plate. Okay, let's go to modify coded and go to shell plate 51. So you see now that the templates are being marked on the shell plate as well. You see what I mentioned, the two markings of the templates. This makes it very easy to identify, to place the templates on the shell plate, because it says how to do it. Okay, the sideline plane is also coded. Okay, so this was in a nutshell the new templates application. We have gone through all the aspects of it: creating, saving, coding them, coding the shell plate that contains templates as well, see the connection between them. And what we will do next is we will see the new Jigs function. There are 3 steps when calculating the optimal jig pillar heights. The first one is to create an optimal jig plane from the 3D model for the larger shell plate panels. The second one is to create a pinching drawing where the calculated height of the pins will be displayed and where we will also see the regular marking lines and the shell plate numbers. The third step is to calculate the optimized position of the pin jig and display them in the view. Let's start now with the first step. In the template step, we choose again New, and this time we will select several shell plates to be used. So let's take a simple example, this shell plate, and a neighbor of his, let's take 52. You can already see now in the HAL viewer a preview of the calculated, of the optimal calculated jigs plane that the system calculates. So this one will be used when creating the jig view. I press now on OK. And note that now the create templates wizard doesn't appear. That is because currently you cannot create templates for multiple shell plates. It only works for single shell plates. So what the system has done now, it has calculated the optimal jig plane. Let's save this template set now. We go to close and say yes, we want to save the template set. Okay, so when you save a template set where you have used multiple shell plates, then the default name will contain both shell plates. So when we have had only one shell plate, then we had only the part number of that shell plate. In case of multiple shell plates, then we have the part number of all the shell plates that we have used. Another very important difference is that here for production information we only have the jig option. So when multiple shell plates are used, we can save for production information only the data saying this is a jig. So I will press on OK. Having created a jig plane, the second step is to create a jig view. To create a jig view, we need to go to Home, choose Perpendicular View, and you will see now that there is a new option called Jig Plane. This option is only available if you have the Jigs license. When you choose the Jig Plane option, then the system automatically reads the existing jig planes in your block. We have now one template set that for plate 51 and 52 that is created as an optimal jig plane. The system fills in the list with the existing template set and chooses the first one as a default. Having a template set chosen, then the system fills in all the necessary information in order to create a view. That is, it uses the point of the optimal jig plane to set the point of the view, and it also calculates the area. This information, as you can see, can still be customized by you. For instance, I will enlarge this a little bit. It's a little bit too precise, 31. And I'll press now on Create. Now, we have now a view where we only see actually the relevant information for us. So as little information as possible, but the complete information of what we needed. So we needed to see the two shell plates because we want to calculate jig pillar heights for these two plates. These two plates are completely visible in the view. We also see a part of this shell plate because yeah, it is until here, until the edge of the shell plate. So part of it is visible, but you see it is not completely visible. What you also see is that actually this view is a regular view. The construction elements are also visible, but we have as little information as possible actually relevant to what we need. The jig pillar heights option is located in Draw, More Dimension, Jig pillar heights. This option is only available if you have the jig license, and it can also be started actually from any shell view. We have now created an optimal shell view only with the relevant information, but it could be started also from a regular shell view. I will press now first on apply so that I can explain the options on the calculated jig pillar height so that you understand better. Okay. Distance between pins allows the user to define the distances between the individual pins of the jig. So you have here from this pin to this pin 500 millimeters, and from this pin to this pin 500 millimeters. Therefore, you can specify both along the length and along the breadth. Of course, you need to fill in a value that is positive. The default in the package is 500 millimeters. In the drawing, we also have here two axes, a horizontal axis indicated by numbers and a vertical axis indicated by letters. You can notice here that the distance between the lowest pin jig from the horizontal axis is actually what we have here as a distance between pins. Then the shift of first pin allows you to offset the first pin of the jig. You can offset the first pin along the length and also along the breadth. Using the shift of first pin, you offset the entire jig to a location within the shell plate. So if I say, okay, the first pin has to be offsetted with, no, not in length, let's say in breadth with 500. I press on apply. You see that everything is now shifted, also the horizontal axis. Then the minimum height. This allows you to set the height of the lowest pin in the jig. This field ensures that the jig pillars are calculated in such a way that the lowest height of a jig pillar is this value. The default value is 100. That means that the plane is also shifted in such a way that we keep the smallest pin. We keep the smallest pin with this value here. The text height factor, this of course influences how the size of the text in your drawing, and this is calculated as textschaal divided by 25. This textschaal is an environment that has a default value of 25. Text height factor must be of course a positive value, and it has a default value of 1. What we also see here is that the system also displays the distance between the minimum pin height and the maximum pin height. this value is calculated when you apply on the button. So it means this is 671. The minimum distance is 100. So it should mean that the maximum pin height is 771. The minimum distance is, of course, where we have more curvature in the shell plate. So it's here, indeed, in the middle. And we should have at the edges the 771 size here. So it is correct. This checkbox here, remove existing pins, it's a very handy checkbox that helps you when you're in the process of determining the exact parameters that you need. Because when you press on apply and you have this checkbox enabled, the old values are removed from the drawing and you have only new values. If I disable this and I say that this breadth value has now no shift for the first pin, then we say apply. You see we have here now 2 times the axis, and the old values are kept. I didn't use such a good example actually, that you see also that the pin values are left, because now they are put on top of each other. So if I press again on apply, now you will see we have now 3 axes and the old values are kept. So I will check this again, say okay, I do not want any shift. It's this because I have used an optimal jig plane, and I press on apply and I get my values, the ones that I want. I think that by now you have guessed what the function is of this button. Apply is a functionality that allows you to keep being in this function and search for the right parameters for your company, for your jig pillars distribution. If you press on OK, then the panel closes. So the heights are calculated again and the panel closes. So I'll do that now and I press on OK. And now we see the distances in our view. Once again, the jig pillar heights are calculated for all shell plates present in the view, and because we also have partly the shell plate, we get for the part that we see also jig pillar heights. I will save now my view. I'll call it jig pillar height. So with this saved view, you can print it and go on your workplace. Because the radius of the jig pillar doesn't change every time you need to calculate the jig pillar heights for several shell plates, but it is specific to your company, the setting of the radius of these jig pillars is a system management setting. So you need to go to system management, and to extra shell, and here you can edit the jig pillar radius. We have a default of 25, but you can customize it with the radius that you have at your company. This concludes our shell plates webinar. For more information, you can consult the help documentation of Cadmatic Hull, or if you have questions, you can contact our support department and they will answer your questions. Thank you very much for watching the webinar.